Hi there, my name is Saruk Karami. Along with Jamal Ahmadi, we are going to give a presentation for our project calling Design and Optimization of a Hybrid Power System for Maris Harbour, Labrador. This project has been done for the MSc project course, which is coordinated by Dr. Mohsin Jamil and supervised by Dr. Ashraf Ali Khan. This project focuses on developing a hybrid renewable energy system for Maris Harbour, a remote community in Labrador that currently depends heavily on diesel fuel. Our proposed system integrates solar PV, wind turbines, battery storage, and a backup diesel generator. We use the Homer Pro for techno-economic optimization and MATLAB for dynamic system simulation. Actually, regarding the result of the project, you can notice here that 88% renewable fraction. It means that 88% of the electricity is generated from renewables. And the diesel reduction is about 45,000 liter, which means huge cost and emission savings. The levelized cost of energy is about $0.192 per kilowatt hours. In this project, we had four main goals. The first goal is designing a cost-effective and low-emission hybrid system. Second is simulating its dynamic behavior, especially under load variation and faults. The second goal is quantifying savings both in diesel use and CO2 emissions. The last goal is evaluating the use of Homer Pro and MATLAB as tools for designing systems in cold, off-grid environments like Arctic. Renewable resource profile. As you can see here, we have a solar PV array for daytime energy and a wind turbine for night and winter winds. And we can use a lithium ion battery bank to store excess energy and smooth supply. A diesel generator is used as backup during low renewable conditions. And all components are managed by energy management system that prioritize renewables and minimizes diesel runtime. Here, as you can see, we modeled the solar and wind resources available in Maris Harbour throughout the year. As you can see here, we have solar irradiance, which is strong in summer. It's about 4.8 kilowatt hour per square meter per day. And as you can see, the solar irradiance is really weak in winter. And when you can comparison the solar irradiance with the wind, you can notice that wind is more consistent throughout the year. This mixture of solar and wind helps stable renewable supplies throughout the season. Here you can see our methodology for our project. Our methodology combines modeling, simulation, and optimization across two platforms, Homer Pro and MATLAB. As you can see, the load profile is built using estimated community energy use statistics. And Homer Pro is used to simulate thousands of system configurations, and it is optimized based on cost, emissions, and reliability. MATLAB, here you can see MATLAB modeled how the system behaves dynamically under changing conditions. And it included battery state of charging management and fault simulations. And about resource modeling, PV is under standard test conditions, which is about 1000 watt per square meter at 25 centigrade degrees. And wind modeled via available distribution at K is equal to 2. Energy management system prioritizes renewable, excuse me, prioritize renewable sources, and it ensures battery state within safe operating limits. Economic metrics, which is calculated in this project, is LCOE and net present cost, internal rate of return, and break-even analysis were all conducted. Here we have control and protection logic. Uh, Actually, regarding battery state of charge thresholds, battery charging limited below 95% and battery discharge stops below 25%. Regarding dispatch logic, energy management system chooses renewable energy first, and diesel is only used when solar and battery are insufficient. Regarding fault simulation, we used MATLAB to simulate a three-phase short circuit, and a breaker isolates the fault in just 80 milliseconds, preserving system voltage. These controls protect both the equipment and ensure uninterrupted power delivery. And as you can see here, the output of the PV output is about 42% of the total output, which is about 38,200 kilowatt hours. And the wind output consists of 29% of the total output, which is about 27,000 kilowatt hours. And the last contribution is battery contribution, which is about 12%, and it is about 10,500 kilowatt hours. This mix shows a high renewable dominance, especially during spring and summer, sorry. In winter, when sunlight drops, the diesel generator plays a bigger role. The battery smooths supply fluctuations and improves stability. Thank you for your attention, and Mr. Jamal is going to present the rest of the project.
Hi there, my name is Saruk Karami. Along with Jamal Ahmadi, we are going to give a presentation for our project calling Design and Optimization of a Hybrid Power System for Maris Harbour, Labrador. This project has been done for the MSc project course, which is coordinated by Dr. Mohsin Jamil and supervised by Dr. Ashraf Ali Khan.
Hello everyone. Uh, I appreciate you for watching our video. I am showing you the rest of our project presentation. We are going to show you the Simulink simulation features. We also had some results getting from MATLAB and also Homer Pro. My friend had provided the Homer Pro simulation results, and also I will provide you the rest of Simulink simulation features. First, we simulated the SOC algorithm over 20-hour and 1-week demand profiles. We simulated the state of charge algorithm using both daily and weekly load data from Mary's Harbors to validate energy balance under realistic demand patterns. These simulations helped us access battery behavior across peak and off-peak cycles and ensured the system maintained reliable performance over short and long during. We encountered some fault scenarios include undervoltage, overcurrent, and breaker operations. Using MATLAB, especially Simulink, we modeled several fault conditions such as inverter, overcurrent, undervoltage at the load bus, and breaker trips. These scenarios tested how effectively the system detects and isolates faults while maintaining continuity of supply through alternate energy paths like diesel and battery backup. Uh, Third scenario we encountered, it was the power converters modeled. Uh, we used a PI controller and hysteresis logic. We implemented PI controllers for controlling generator frequency, battery voltage, and wind turbine pitch angle. Hysteresis logic was used in inverter control block for fast switching decision during protection event, enabling responsive and stable converter behavior under dynamic loads. Uh, Also, we had the SOC behavior within safe bounds across all seasons, 20% to 95%. The battery's state of charge remained within a safe operational range of 25% to 95% across all seasonal profiles. This reflects proper sizing and load balancing in the hybrid setup, avoiding deep discharge or overcharging conditions throughout the year. Here now we have the key simulation result of both Homer Pro and Simulink in MATLAB simulation. The wind turbine contribution of making power, it is for around 95% of total energy demand. Solar PV contribution is already my friend showed you. It's around 6% of total energy demand. You can consider the wind is the dominant in Mary's Harbour in Labrador. Battery storage capacity supports intermittent generation and peak shaving. Diesel generator contribution, it's a backup profile which used only for emergencies. It's around 0.2%. Total net present cost of using this project is around $3.5 million in Canadian dollar. Levelized cost of energy, LCOE, it's around 20% for each kilowatt hours. Annual diesel fuel consumption, it's around 45.6 liters, nearly eliminate. It was around nothing. Now we are going to show you the economic analysis we got from Homer Pro. Here we have the capital cost of 954 hundredths, which equal to around 1 million Canadian dollar. Operation and maintenance cost, it's around 2.5 billion over lifetime. Replacement cost for this project is around $1 million. This $1 million includes the replacement of batteries, inverters, and components with limited lifespans over the project duration. The break-even year for this project is a year of 7, which means the system becomes more economically than diesel-only operation starting in year 7 due to fuel saving and lower operation expenses. Total saving for this project, it's around 820,000 compared to diesel only. We have the LCOE cost for this simulation for Mary's Harbour. It's around 20 cents kilowatt hour versus 32 cents kilowatt hour for just using diesel. The internal rate of return remains strong, even we accounting for expected future increases in diesel prices, making the project a viable investment. Okay, next slide. We are going to show you the environmental impact of simulating this project using renewable energies with a 100% renewable portion of our resources. We have a diesel consumption reduced at 45,000 liters per year. We reduced the CO2 emission around 95,000 kilogram per year, avoid carbon cost around 24,000 Canadian dollar per year. Also, the project directly supports Canada's objective for lowering greenhouse gas emission in off-grid, indigenous, and northern communities. Our model is scalable for 25 or more than 25 years similar remote settlement in Newfoundland and northern Quebec. The architecture. Sizing logic and control system can be customized for similar demographic and climate condition, making this solution scalable and replicable, which means we can use this project for remote areas with harsh weather and something like that. Our next slide is about the future expansion scenarios about simulation and how to implement a project like this. We could add a 10 kilowatt PV, which are cost effective at least around 15 cents per kilowatt. If panel costs continue to fall, adding more PV capacity could further reduce LCOE and increases renewable fraction. Introduce predictive EMS with load forecasting, which is a machine learning based. Future work includes using machine learning to forecast demand patterns and improve dispatch decisions in real time. Upgrading inverter to smart system will allow better voltage control and reactive power management across the microgrid. Next future, we aim to implement adaptive control strategies that reprioritize sources in real time depending on changing load and weather conditions. Finally, collaborate with indigenous communities for social acceptance, social integration, and manage engagement with local indigenous groups are essential for long-term success and sustainability of this project. Based on our each engineering project, we got into the conclusion slide of our project. I mean our simulation project. We designed and validated a fully integrated hybrid system tailored for a specific load, climate, and economic context of Mary's Harbour. In most scenarios, renewable sources contribute over 85% of energy, with diesel serving as a last resort backup. Annual diesel use is reduced by over 45,000 liters, cutting CO2 emissions by 95 or 96,000 kilograms per year. Also, we got that Homer Pro simulation were critical for techno-economic optimization, allowing us to find the best cost to performance ratio. Simulink was used to implement real-time control blocks and verify system behavior under fault, disturbance, and load variations. This model can be adapted for a similar remote Arctic and substract communities with slight modification to reflect local resources and demand. This model is scalable for other off-grid settlement across Labrador or beyond. Sorry, at the end of our project. Thank you for watching and patience. Hello everyone, again, I'm Jamal and I want to show you the rest of the project through the Homer Pro simulation, and also we had a project for Mary's Harbour here in Newfoundland and Labrador, Canada. Sorry about my screen, because I have to use a remote access to the Homer Pro because I have MacBook, and unfortunately Homer Pro doesn't support Mac OS, uh, uh, Mac OS, and also I had to use another platform. It's not a big problem. Here I want to show you the load profile, also our simulation. Here we have a component here. First, I want to start with the load profile. Here we have a load profile. As you can see, the peak time for our load is between 9 at the morning through 18 in the afternoon. And the average of our load is around 850 kilowatt hour per day. It's a AC load. And also you can see here the distribution of the load through a year profile. The next one, I want to show you the wind turbine. Here we have a wind turbine, which is a general wind turbine. It's 95 kilowatt power generation. We have a capital cost for constructing the tower, and also something to do is around 300,000 Canadian dollar. Operation and management cost per year, and also the replacement cost we have here. I can scroll down here. You can show the wind turbine selected. It's hand turbines. Also, we can have the load. We can consider the lifetime for this as 20 years. Hub height, which means that this turbine will work at 38 meters. The next component we have, it's a backup generator. Here we have a 100 kilowatt fixed capacity, a generator with a fuel curve interpret or fuel consumption 2.8 liters per hour, and another specification of this backup generator. You can see here the emission, fuel properties, and another types. Also here for this profile, for this component, we have a site specific, another implemented data. Finally, here we have a DC bus. It's for our PV array, also our batteries. Okay, we have a PV array. We want to we want to have our implement 25 kilowatt capacity array here, which the capital cost for this array is around 35,000. Replacement cost, also operation and maintenance cost we have here. We have to consider the duration factor, it's 85%. Also here we have the efficiency factor of this array is around 70%. Another specification here, rated capacity for this array is 25 kilowatt. And the battery backup or battery storage, battery bank here, we have a nominal voltage. We select the 6-volt batteries. Nominal power capacity is 6.91 or around 7 kilowatt. And maximum capacity. Also, we have the capacity ratio, round trip efficiency, another specification. The total cost for a quantity of 400 batteries for each one, it's around 1,500 replacement cost, and also we have the operation and management cost here. Finally, we need a converter to connect the DC bus to the AC. We use a Kihua France KFBCS 100 kilovolt ampere. It's a general kilowatt, general inverter through the Homer library. The capacity is around 100 kilowatt. The assumed capital cost is $20,000. Also, the replacement cost is as the same. The capital cost is 20,000. Operation and manage cost is around 1,000 Canadian dollar per each year. We have a lifetime for these inverters, 10 years maximum. Efficiency 97%. Also, if we want to use it as a rectifier, we have the specification here for the rectifier. Now all components are set: load, backup generator, wind turbine, and the DC bus. We have here a PV array, battery bank, an inverter one. Finally, we want to calculate the optimization for this system. I tap on the calculate here. Homer Pro is starting to optimizing. Okay. Here, I think we have two profiles here. Base case, lowest cost system. Okay, we go through the optimization profiles here. Okay, we have here three tables of optimization from Homer Pro. As you can see here, the optimization didn't consider the PV array. Here, consider PV array, wind turbine, backup generator, and another option. Okay, we want to choose this one as a best option, which the LCOE levelized cost for this optimization is around 19 cents per each kilowatt hour. The net present cost for constructing and also doing this project is around 3.5 million Canadian dollar. I go through the selected profile. You can see here total net present cost is around 3.5 million Canadian dollar. Operation cost is around 45,000. We have the cost type and categorized type cost. We could consider the cost type. We have here the capital cost, operation cost, replacement cost, and also salvage cost. Also, we can consider the cost by component. Here we have the generic 100 kilowatt fixed capacity genset. It was the backup generator. It's the converter or inverter. Other costs uh, generic PV, and wind turbine. Okay, I want to go through the electrical section. You could here see the production of power, which is the PV array, which produced the 29 kilowatt, 5.68%. 94% of our production is for hand M2495 kilowatt wind turbine. You can see we have a 100% renewable fraction for this project. Also, you can consider the power production of um, backup generator. It's around 125 kilowatt. It's not considerable. It's already zero. And also we here have the production profiles for each month: January, February through December. It's demanding. I have to mention one point that Newfoundland, the Canadian provinces, has a dominant wind, which we can consider all areas for its good area or good locations for using and providing wind turbines. We have at least, I think, 8 meters per second wind speed at the lowest area, at the lowest speed. We have that. Okay, here we have the fuel summary we mentioned previously. It's total fuel consumed. It's around 46 liter per year. Here we have around 0.12 liter per day. It's also we can have the renewable penetration. Here we have the total renewable production divided by load. Another point I forgot to show you. We have here 30.1 excess electricity. We can consider it as a public heating, public lighting, school, some areas that are public. We can use as a we can produce heat through this excess and sell the heat to the customers. Okay, here we have another profiles. We can consider them, and as you can see here, based on our Homer Pro optimization, you can consider which one is the best option to implement through that geographic area. Also here we have our constraints here, which we considered for our project. Minimum renewable fraction we consider as a 60%. Also solar power output we consider it as 15%. Wind power output we consider it as 80%. Thank you for watching and also for your patience during our presentation. I hope this was a useful project for you. I will upload it through our channel, and if you have any question about our simulation, our providing data, and another, I will answer to your question. Also, finally, we had here some resources like a solar GHI for the Mary's Harbor, which it is here already. We considered it solar DNI, wind speed, and other factors. Thank you, everyone. Have a good time.